Hello everybody and welcome to today's AIRAH webinar. My name is Marie Karakala and I'm AIRAH's Engagement and Program Coordinator. Today's Streamline is brought to you by AIRAH and Ecolibrium, and this webinar will look into the NCC 2019 Section J of Case Study of Ducts. Before we get started today, if you've got any questions, please type them into the Q&A function, which is located just at the bottom of your screen there, and we will try our best to get through as many questions as possible at the end of the presentation. So now I would like to introduce to you our presenter for today, Ken, who will be taking us through today's session. So Ken, I will pass things over to you now. Thank you.
Okay, well, let's get started. Thanks very much everyone for joining me today. We're going to go through the code in regards to ductwork. Ductwork obviously links to the fan compliance requirements as well, so it's not just around the ductwork, it's the fan compliance as well. So we will be working our way through all of that. So I will highlight some of the aspects where the fan compliance links in. So the relevant clause in the code is Part J 5.5 of Section J. Remember, this only covers the ductwork compliance requirements. There are other requirements in the code that address the remaining aspects of the HVAC airside systems. One of them was covered in the previous webinar, J 5.4, which is fan system or fan efficiency, which links to the ductwork design in regards to pressure losses in the ductwork. This webinar is focused on ductwork, insulation and sizing impacts of the building design on the ductwork system. So to understand the application of Part J 5.5, it's important to have an understanding and be aware of the requirements of other clauses in the code, J 1.1 and the building envelope, and J3 are the two important parts in the code that impact on the ductwork sizing. So we will go through those to start with. We're looking at clause J 1.1, the application of the part is to the building envelope. So what we're talking about is the building fabric, which forms part of the building envelope, and that building fabric will be required to meet an R value, and that R value has to be applied to all class 2 to 9 buildings for any aspect of the building fabric. The building fabric is the roofs, walls, floors, ceilings that separate the conditioned space or habitable room from the exterior of the building, the non-conditioned spaces in the building, the floor of a rooftop plant room, a lift machine room or the like, the floor above a car park or warehouse, and the common wall with a car park or warehouse or the like. So these are parts of the building envelope or the fabric, the building fabric that forms that building envelope. The ductwork clauses that we are required to meet are based around the ductwork and the fittings in an air-conditioned space. So the conditioned space and the air-conditioned space do not quite have the same definition. The air-conditioned space is where we're applying active air conditioning to a space, while a conditioned space may not have active air conditioning applied to it. So we have to look at the ductwork for an air conditioning system and where it sits within the conditioned space and comply with the Australian Standard 4859. And we have to have an insulation R value greater than or equal to, for flexible duct, an R1, and for the cushion head box that connects to any ductwork, the same as the ductwork. So this is simplified from previous codes. It is just R1. So all flex ductwork is R1, irrespective of where it is located, whether it's in a conditioned space or a non-conditioned space. And the cushion head box, if connected to the flexible ductwork, will be R1 as well. The defining factor there is the fact that it's connected to the flexible duct. If that cushion head box is connected to some hard duct, then it must be the same insulative value as the hard duct to which it connects. Otherwise, the ductwork requirement for insulation is as per the table J5.5. And I've got a copy of the table there. You can see the values based on climate zone and the location of the ductwork. So whether it's in a conditioned space, exposed to direct sunlight, or all other locations. The all other locations isn't defined in the code, so that does require a little bit of interpretation or application of where that all other locations is, and that's why I mentioned before about how we define the conditioned space. It's quite important. So if we're defining the building envelope, as I mentioned before, it's made up of the building fabric that are the structural elements and components of the building envelope. And looking at the diagram we have here from the Building Codes Board, supplementary information back from 2006 when Section J was originally devised. There's not been any significant change at all since then in how the Building Codes Board interpret the envelope line and what parts of the building fabric would need to meet the requirements of parts J1.1 and part J1 and J3. So we need to have a fair handle or understanding on this before we jump into determining what our ductwork insulation is going to be. In this diagram, the envelope line is represented by the blue dotted line. The plant room is not provided with active air conditioning, and the stair is not provided with any active air conditioning. Both these spaces would strictly be considered non-conditioned spaces, and therefore the internal walls surrounding these spaces would be required to have insulation and sarking to ensure air leakage is controlled and the walls are insulated. So, in other words, they must comply with parts J1 and J3. The ductwork in the plant room would therefore be considered in all other locations. So if we went back to table J5.5, we would see it's all other locations and we would determine the R value based on that. So the location of the insulation in the building dictates the insulation requirement of the ductwork. Now, in different types of construction and different types of buildings, we have, say, a steel frame building or a all timber building or a brick veneer style timber construction as examples here, and then also concrete tilt panel construction. Now, depending on the type of construction, will vary where and how insulation can be applied to the building fabric. The limitations on where and how we apply insulation to the building fabric may have an effect on where and how we can determine what space or whether our ductwork is in the conditioned space or non-conditioned space. So we need to have an understanding of the construction type or methods that are going on in our building, just so that we can make sure we're applying the correct ductwork insulation requirements. So here's just a couple of alternate examples or options in regards to consideration of the building fabric. Looking at the options here in respect to the envelope, in our first pass, as per the previous slide, I had the plant room is outside the envelope and the internal stair is outside of the envelope. You may consider both the plant room and the stair to be inside the conditioned space or inside the building envelope by, from the diagram on the right-hand side, you can see I've got the yellowish lines which go around the outside of the plant room. So I have moved the envelope line to the outside of the plant room. And I have deleted the need for the requirement of the envelope around the stair. In this instance, we're allowing a bit of infiltration air from the adjacent conditioned spaces to go into the plant room and the stair. And this may be appropriate based on the construction methodology of the building and the ability for the builder to build in accordance with J1 and J3. So in some instances, it may simplify the construction of the building, and this simpler approach may also benefit the insulation requirements for the ductwork. So if we have another option or look at another consideration, we may adjust where the envelope line is in regards to the ceiling plenum. So in the instance where the ceiling plenum line defines a, where the, envelope line is defined and it goes around the space and is based on the or is fixed to the underside of the plant room. It would depend on whether we're applying the insulation and or sarking, if required, to the underside of the slab or to the ceiling line. Insulation applied directly under the slab means the envelope line's at the slab line and the ceiling plenum is within the conditioned space or within the envelope. Insulation fixed to the ceiling means the envelope line is at the ceiling and the ceiling plenum is outside of the envelope and therefore is non-conditioned space. So we need to consider what the implications are of the construction of the building on our ductwork insulation. So we need to look at things like the available ceiling space, the type and application of ductwork insulation itself, and then the different types of building and ductwork insulation that are used. We have more or less opportunity for our ductwork and the available space for that ductwork based on whether we can fit all of the insulation into that available ceiling space. So we'll run through a case study example a bit later on, but in the case study example, there's an instance where we only have 250 millimetres clear space available as per the sketch, where the ductwork can run because of structural beams, light fittings, etc. in the ceiling space. So these things need to be considered when doing your ductwork design and how they might impact on your static pressure calculations. So having an understanding of what is available or what options there are for both the building insulation and your ductwork insulation may help you solve some spatial constraint issues on projects. So let's have a look at the case study. Bit of background information on the case study. If we're looking at a small office building, there is a pinch point in regards to ductwork getting from the plant room to the ceiling space. It's not a to-scale drawing or anything. It's just indicative. The office space is approximately 500 square metres with a supply air requirement of 2,400 litres a second and a return air 1,600 litres a second with 800 litres a second of the outside air. As you can see in the diagram, there is a dotted line around the outside of the building which represents the envelope line. There is some insulation applied to the underside of the slab under the plant room. This may or may not be necessary depending on your building design, but in this instance there was insulation applied under the plant room slab, and the enclosed ceiling space had the ductwork and supply air into the system, into the space. So the location of the insulation in this instance is around the external fabric line of the building, up the wall, along the roof line, and then around the outside of the plant room. So the plant room would therefore be included in the conditioned space in this particular application, and the plant room is being noted as being a tempered plant room. So we have a pinch point here where the structure, there's an edge beam there obviously supporting the plant room, insulation, ductwork, light fittings, structure, all trying to get through that tight little location around the perimeter edge of the plant room. This makes it rather difficult to get ductwork from the plant room across that ceiling and into supplying the into the ceiling plenum above the conditioned occupied zone. So now we have a bit of an understanding of the building insulation location. We do know what we need to do with our ductwork insulation. All of our ductwork, all of our supply air ductwork in this instance will be considered to be in the conditioned space. But I'll also, through the case study notes, actually demonstrate or do a bit of comparison if it wasn't to be considered in the conditioned space and the ceiling plenum area was not part of the conditioned space, that it does have an impact on your duct sizing and reduces your duct or your options in regards to your duct design. So now let's have a look at the duct design and particularly around that pinch point. But first of all, let's just look at duct design and duct locations in general. From the guide on the Building Codes Board's website, on the NCC website, there is examples in the code, and the diagram on the left is an example that they've provided in the supporting documentation. We have an air handler sitting in the corner of a plant room, and it's supplying two spaces, space C and space B. Space A is the plant room. So the ductwork that is in space C, which is the last room being served by this particular air handler, doesn't actually require any insulation. This is a supply air ductwork. If there was return air ductwork in space C, then it would also not require insulation because that ductwork would be considered in the conditioned space. And return air ductwork within a conditioned space does not require insulation. Space B, because potentially space B could be off, or the air conditioning to that space could be turned off or isolated, and space C could still have air conditioning, then the ductwork is required to be insulated through space B, but it's insulated as though it's within a conditioned space. And then space A is the plant room, which is outside of the envelope in this instance, and therefore would be an R2 insulation requirement. For ductwork, and this is where it links into the requirements for fan efficiency. For ductwork, the index run across all sections of the straight rigid duct must not exceed 1 Pascal per metre to meet code. So that will affect the calculations, which I'm going to go through. So here's just a quick example of ductwork sizing. If I have available space, as per the previous diagram, we said it was 250 millimetres available space. And then we put internal insulation on the ductwork. We have, say, 40 millimetre internal insulation top and bottom. Therefore, we have an air path for our ductwork of only 170 millimetres in depth. And if we were to not exceed the 1 Pascal per metre, we can then have, and we're to try to keep our duct ratio to a reasonable ratio of, say, 4:1, which is quite a reasonable duct aspect ratio. About 8:1 is the limit on what you would apply as a duct aspect ratio, because beyond 8:1 you start to get some significant airflow issues within the ductwork, and the entire ductwork isn't actually used or transports all of the air down the duct. So there are some physical issues that occur once the aspect ratio gets too large. So if we stick to a reasonable aspect ratio of only 4:1, this ductwork at 170 millimetres air path can only accommodate 513 litres per second. Or if we used a different type of insulation that was 50 millimetres thick, then we're down to only 400 litres per second. So you do end up being quite limited in the air capacity of the ductwork. And this is also reflected in the static pressure losses that will occur through fittings and bends. With aspect ratios of greater than 8:1, as you can see for fitting number 021, you can see that the aspect ratio, the maximum aspect ratio that's put in there for a determination of a KT factor is 8, or the minimum one is 0.25. 0.25 in this instance equates to the 4:1 ratio that I was talking about before. So that's the height to width ratio. So you can end up with significant static pressure losses based on KT factors of fittings, etc. In this particular example, in the case study example, with the 2400 litres a second, if we were to put one piece of ductwork going through that available space at 150 millimetres in depth, and try to achieve just the 5 metres per second air velocity, which keeps the pascals down to about 1 Pascal per metre, we actually end up with an aspect ratio of 17.7:1. So the ductwork ends up 2,650 millimetres wide. Ductwork of that width becomes rather costly to make. You will require additional hangers in the mid portion of the duct, typically because 2,650 millimetres in width is not really self-supporting because ductwork is sheet metal, and you'll need additional supports on the duct and additional hangers. And with ductwork of that width, it can sag or bend in the middle and create low spots. Those low spots allow for a build-up of any moisture or dust or contaminants, and this could potentially cause a health risk. So it's and it's also very difficult to install ductwork of this width. More than about 1500 in width starts to get rather difficult to install, just because the physical limitations of a person trying to actually hang ductwork of that width and that size. So in this particular case study, if we were to stick to that spatial requirement, we do end up with quite a big problem in being able to bring one piece of supply air ductwork out under that pinch point, and this will create a rather large issue in regards to our design of our ductwork system. And also the aspect ratio of 17.7 to 1 will result in all your bends and fittings in that location or near that area having very high pressure drops. So potentially a solution might be to only locally shrink the duct or to use multiple supply air duct. So if we have a look at the sizing maximums, if we were to go for this particular pinch point, if we were to look at the sizing maximums, for a 4:1 ratio, we are limited to about 513 litres a second, and then for a 8:1 ratio, we're still at around 1200 litres per second. So the 2400 litres per second would need to come out of, say, 2 supply air ducts through that pinch point area, or we would need to consider some other design change. So it does get rather complicated and rather tricky, and then we may consider removing insulation on the ductwork in that area and doing a performance-based solution of some sort. But you do have to start looking at your options when you get to these pinch points and how it's going to work from a design perspective. So there is some trouble in trying to work out what we're going to do. So let's have a look at a couple of possible solutions here that we might be able to use, because we don't want the design of the ductwork and the insulation requirements of the building and the insulation requirements on the ductwork to result in our fan selection being non-compliant and us being unable to find a fan that will meet the efficiency requirements of the code. So that's the bump-on effect, that if you can't get a reasonable ductwork design with reasonable aspect ratios, then you will end up with static pressure losses in the ductwork that are likely to exceed the code requirements, and then you will potentially be unable to get a fan selection that meets the efficiency requirements. So we've got limited ceiling space, as we noted before, due to that pinch point. We only have that 250 millimetres. If we're to do that in one piece of duct, it's a 17.7 to 1 aspect ratio. So that's not going to work. That's not a solution. We're going to need to consider, as I mentioned just before, do we do 2 supply air ducts? Do we remove some of the insulation just locally at that pinch point, make the ductwork bigger where we can, and then just have it come down to the pinch point and then again get larger after the pinch point where it's gone underneath the girder. So we should consider all these options in our ductwork design, And if necessary, we may have to do a performance-based solution on the insulation, and maybe make the insulation slightly thicker on the rest of the ductwork, where we have more space, and remove or have very thin insulation at the pinch point, so that when we have a higher, larger amount of space at the 250 mil, we might be able to achieve 220 mil or more by using a different type of insulation material. So it's something to consider. You need to go through and actually look at all this sort of stuff and see what ductwork solutions are achievable on site. So one other solution to sort of look at, these are possible compliance-based solutions that you can go through and the options you have. This is not exhaustive. I've just got 2 or 3 options here for consideration on how we might solve this issue. One is, in this particular instance of the case study, this may not work, but if you are non-compliant on your ductwork, so you allow your ductwork to run harder and faster, particularly locally at that point, you can reduce the aspect ratio on the ductwork, and also you can then potentially get a much more efficient fan in the installation, and that may compensate for the higher static pressure that's occurring locally at that point, and you may still be able to achieve compliance on a system-based approach. So you have a watts per litre per second allowance on a systems-based approach. That's a combination of the ductwork static pressure losses and the fan efficiencies, and then you can compare that to your selected fan efficiency, and if you can still achieve a better fan efficiency, you can achieve compliance at a system level. So that's possible, in particular using the ABCD calculator. It's a good way to try to determine a solution there. Otherwise, you can look at different air conditioning systems. So in the case study, we had a fully ducted system, and we had a pinch point, and we had some difficulty being able to get ductwork through that pinch point. If we change to a VRF or VRV style system, then we only have pipe work potentially going through that pinch point, and we could have direct ducted the outside air into the space for a DOAS system, direct ducted outside air, or we could think of some other solutions, or because we're only considering the outside air into the space, that may now not present a problem, as we only had 800 litres a second of outside air in the case study. So that doesn't present as much of a problem going through that pinch point. We could still get a reasonable aspect ratio on our duct. So we may do that. So that's another option. You change the type of system and the arrangement. Otherwise, and as I've mentioned before, you can look at different insulative materials, some high density foams, and other products have R values that are equivalent to normal glass wool insulation, and provided they meet the AS 4859 requirements, then they can be used as alternative products. You may have to do, or you may reduce the insulation requirement locally at the pinch point. But any of these things are reasonable options to consider. So going through your duct design and duct solution and looking at those specific pinch points, etc. So you can you have options, and it's just a matter of going through the design approach. You could also do an energy analysis on the system and do a comparative energy analysis between your design system and the deemed to satisfy proposed system. That doesn't necessarily need to be done in an energy modelling software. It may be done via some other alternative assessment method or approach, and you can then get a solution that may work for you. So in conclusion, this one's gone rather quickly, which is good. So in conclusion today, I'd just like to highlight that understanding the building envelope, where insulation is required in the building envelope, where the building envelope is defined around a building, does impact on your ductwork design. So you do need to have an understanding. You don't need to be defining the building envelope. That may be done by the sustainability consultant or the architect, but you do need to have an understanding. You do need to check it. You do need to possibly make suggestions back to the builder that it would be easier if the envelope line was in this location and not that location, and have an understanding of all of this so that you can optimise your ductwork design. The impact of the aspect ratio on ductwork, so going through pinch points or having spatial constraints on where the ductwork can and cannot fit. It's important to take into account aspect ratios. You do not want really wide, flat duct. It doesn't work very efficiently, and it can really add some issues in regards to fan performance for your system. You can use compliance pathways such as the fan calculator and system compliance via the fan calculator to get compliance for your ductwork. You can look at other alternative methods, performance-based approaches, energy analysis, calculations, alternative design methodologies, alternative products, as long as they meet the compliance requirements within the code, so they meet the governing requirements of Section A of the code. And then you can present those alternate solutions as your solution, or those performance-based solutions, or consider different air conditioning systems and types that don't have the same spatial constraints and spatial requirements as ductwork does, to limit or reduce the amount of ductwork you're supplying to a space. So that's all I have on ductwork for today. If people would like to keep asking questions, I'll see if I can answer the questions that are coming up online. So in regards to flexible duct insulation, the question is that R1 applies to all types of buildings regardless of conditioned or non-conditioned spaces? So R1 is insulation that, R1 is the R value that's required on flexible ductwork that is part of an air conditioning system. So it doesn't matter, as long as it's class 2 to 9 buildings, then that's what we have to comply with. So in class, oops, sorry, 2, just move that over to there, 2 to 9 buildings and all. So the enclosed, sorry, Matthew missed it. Can I confirm the enclosed ceiling space from the the example was considered conditioned space. Yes, in that particular, in the case study example in the slides, it is in the conditioned space, as the envelope line was up the wall and then across the roof line, and not the ceiling line. So in that instance, yes, the enclosed ceiling space was within the envelope and therefore considered within the conditioned space. Climate zone 6, where the AC ductwork is installed in the roof space under roof insulation. So simple answer is yes. However, it is not just the insulation, the building envelope insulation. It's also the sarking. So there does need to be sarking at the roof level to ensure that we are meeting J3 compliance as well. So you do need to comply with both on that roof line. And then yes, that ceiling space is within the conditioned space. Again, ceiling space status in regards to conditioned space. So this question's come up 3 times now. So it's obviously quite a point that people really want to understand. So yes, it all comes back to the envelope line. Where is the insulation and the definition of the envelope line? In the majority of instances, particularly in high-rise buildings, the envelope line will be the external fabric from slab to slab. Therefore, the ceiling space that is within that envelope line ends up within the conditioned space. If you have a rooftop ceiling plenum or rooftop ceiling space, that the insulation is applied at the ceiling line and the roof is only partially insulated or not insulated much at all, then you have a non-conditioned space for that ceiling void. So there are instances where you will have a non-conditioned space for that ceiling void, but it doesn't occur too often. Apartment buildings, particularly townhouse style developments or aged care developments, etc., do tend to have ceiling spaces that would most likely be considered not in the condition zone. So just so the other answers, but yes. I did mention that insulation can be reduced locally in ductwork. It's not stated in the NCC, it is a performance-based solution. So if you locally reduce insulation in ductwork, you may compensate for that by slightly increasing the insulation requirement on the other parts of the ductwork. And then via a fairly basic calculation, you should be able to demonstrate that you haven't, the average insulation overall would still be better than compliant to the requirements within the code. So the answer to that is quite long, but it is a performance-based solution. And you need to provide calculation and evidence. So it's not stated in the NCC, but you are allowed to do performance-based solutions as per the NCC requirements. So you can achieve a result by doing that performance-based solution. So there is a question in regards to the fan ducting options. So when is a fan ducted and when is a fan not ducted? That was part of the fan webinar. So we'll just leave that one for an offline answer. The duct within the building envelope can still run into an unconditioned space, which could be pretty hot. It would not make sense to reduce the duct insulation. No, it wouldn't. And yes, ductwork that goes from a conditioned space into a non-conditioned space does then need to be insulated in accordance with the requirements. So that non-conditioned space could be pretty hot. The diagram that was in the supplied by the Building Codes Board is under the assumption that the majority of the time those two spaces, space B and space C, would actually be air conditioned. However, there would be some instances where that space B and the ductwork running through to space C, space B's air conditioning may be off. So to reduce the energy loss, the insulation is required on that ductwork going through space B because sometimes space B may not be air conditioned. So that's what that's about. It's not about completely eliminating any energy loss or something of that nature. It's about reducing the energy loss and making the system more energy efficient, but also taking into account the fact that it doesn't happen all the time. If that ductwork, if space B was a non-conditioned space and was never air conditioned and air conditioning is not ever on, then it would apply the insulation requirements for a non-conditioned space, so all other spaces. I hope that so I hope that answers that question. A duct within a building envelope can still run into a conditioned space. Oh yes, so it's live, done. Is the 6 metre flex ductwork R value shall be the same as ductwork or R1? No, so the 6 metres of flex, as per the clause, is R1. All flex ductwork is R1. That's the clause now. It was simplified for 2019 because of requests by the industry and a push by AIRAH. So yes, R1 flex duct is it. That's it. R1 flex. All flex. There is a maximum amount of flexible ductwork in an index run of 6 metres. 6 metres per, well, it's per duct run. So it's not necessarily the index run, but it's per duct run. So any supply duct run to a supply point can only have 6 metres of flex duct. So each supply point can have 6 metres of flex duct to it. You may have 5 supply points into a room, you hard duct to that room, and then you've got 6 metres of flex to each one of those supply points in that room. But it's 6 metres maximum on any duct run, so from the supply point back to the air handler. Same answer, 6 metres. And it's no difference in the in the insulation requirement, whether you do a 3 metre piece of flex or a 6 metre piece of flex. So if you've got production facilities and you've got equipment that is specific for a production equipment or such like, under the code, we don't, if it's process related air conditioning, so for a production of something and it's specific for the process, then the air conditioning system for that process doesn't need to comply with the code. So that's the ductwork and everything. So if it's process related, you just need to determine in your production facility, is it process related and the air conditioning is specifically applied for the process, or is the air conditioning applied for the people in the room that are doing the production but not the process itself? Then the people in the room are the ones being provided with the air conditioning, and the air conditioning system still has to comply with the code requirements. So it's project specific really, and application of the HVAC equipment. So yes, someone's asking again about the fan calculator. This is the webinar on ductwork. The fan calculator does have 1 or 2 issues in it that are minor. I would personally rely on my own engineering calculations and use the calculator for compliance purposes. But that's my personal opinion. You could probably rely on it if you like. So it's really up to you. Sorry. And engineering assessment and judgment. If you rely on the ABCB calculator for anything and everything that you design and do, you do need to be able to ensure that you verify that yourself and you're happy with it, because it's your certification or engineering qualifications and your ethical requirements. Yes, the envelope definition is a bit different to the normal day-to-day work. Yes, so if we're looking at an apparent need for clarification, what I have noticed is that the guide has got a large amount of clarification in it now, particularly around the envelope. And there are additional resources online that help clarify all of these items. So it is a matter of not just sticking to the code and looking at your interpretation and how you apply the code. You can use the guide and other documentation. Also looking at attending these webinars and looking at the case study that's available through Ecolibrium and AIRAH. You can also help yourself in being able to clarify these items. What if we need to have more than 6 metres of flex duct? Any solutions? Do a performance-based solution. You will need to demonstrate the energy efficiency difference or lack thereof, or energy efficiency improvement that you can achieve by using more flex if you wish. So can I confirm rigid duct can be used between the 6 metre, say you go 3 metres of flex, a bit of rigid duct, say to get through a, I don't know, firewall or a penetration or whatever that you need to get through, and then you put another 3 metres of flex on. As long as it's in accordance with the Australian standards and the ductwork standards and the code requirement of a maximum of 6 metres of flex, then it's up to you as a design engineer to determine that that's acceptable. So I cannot confirm nor deny, but I would, in certain situations, possibly use that solution myself, but I would not use it in too many applications. I'd prefer to go rigid duct and then just standard flex. It's a bit easier to install, you get less air leakage problems, you get less performance issues, etc. But yes, so up to you as a designer. Does it apply to data center AC systems? Well, data center AC systems are directly process related cooling requirements and are not there to condition the space for occupants or anything. So typically no, but there are some aspects of Section J that still have to, your data center area or etc. will, excuse me, have to comply with. So I'd just have a look at that. Typically with data centers though nowadays, because data centers are going for very high PUE performance, etc., you'll find that the energy efficiency that you are driven to by the client and designer of the client of the data center is far in excess of anything Section J would push you to. So what insulation R value is required for the preconditioned air ductwork in conditioned space? So not sure how to answer that question because it depends on the design of your system and what duct you're using for where in the application, whether you're using exhaust duct or whether you're talking exhaust duct, return air duct. Supply duct has to meet the R value requirements. Return air duct and exhaust duct doesn't have to be insulated as per Section J requirements, but if you're trying to achieve a certain efficiency on your heat exchanger or preconditioning setup, then you may want to insulate that ductwork. Difficult to answer without actually seeing a full design of the system. Building shafts. Okay, so that's a very good question. So in the example I actually gave where I had the stair and I said potentially the internal stair could be within the building conditioned space and the envelope line could be around the absolute external part of the building. If you've got a, and I did this on a project, I had the ductwork riser come from the rooftop plant room down 15 levels of a building, and at each level it came off and supplied supply ductwork was into each of the floor levels where it bumped out. Now, strictly speaking, the ductwork riser would be outside the conditioned space. What we did as a considered solution, using just a bit of expert judgment, and decided that if we insulated the top of the riser, fully enclosed the top of the riser and sealed it up where the ductwork went into the riser, so that then the riser was separate from the plant room. Then we decided that we would make the riser, the ductwork riser, part of the conditioned space, because that actually made the ductwork riser smaller and allowed us to reduce the insulation requirement on the ductwork. And that ductwork leaks. You can't typically get any ductwork that doesn't leak some sort of air out of it. So the riser would end up getting a tiny bit of air-conditioned air in it. If it's a fully internal riser that doesn't see any sunlight, it doesn't have any external load on it because it's adjacent to all conditioned spaces. So therefore, you find that the temperature in that riser would stay very stable, and we could realistically consider that it probably is part of the conditioned space. So no, it doesn't necessarily have to be all other locations. It could be within the conditioned space. But you need to discuss that with the builder and how the builder's building the riser. That's all of the questions we have.
Thank you, Ken. Good work getting through all those questions. So we might wrap it up there, everybody. So thank you to everyone who registered and attended today's webinar. A special thanks to you, Ken, for a great presentation once again. Just to let anybody know that the webinar has been recorded and it will be made available up on the AIRAH website over the coming days, and I will send out an email and let you guys know when that does become available. So thank you everyone again, and if you want to register for any of other AIRAH's upcoming webinars, please visit the AIRAH website. We do have a few webinars still remaining for the end of the year, so feel free to check those out, and we look forward to seeing you again next time. Thanks everyone. Thanks, Ken.
Thank you. Bye.